Professor. Good morning, everybody. I am Giuseppe Desiderio. This work has been developed in collaboration with the University of Birmingham and Techne, a company managing infrastructure in Italy. And the title of the paper is Image-Based Multi-Damage Detection in Tunnels, a Deep Learning Dataset for Structural Health Monitoring. In 2022, the Italian Ministry of Infrastructure and Transport has introduced the new guidelines for the classification and management of risk, safety evaluation and monitoring of existing tunnels. The objective of these guidelines is to provide a methodology aimed at promoting a proactive maintenance approach by establishing safety benchmark based on the so-called classes of attention. The guidelines are divided in 5 levels. In this presentation, we will focus specifically on level 1 on-site inspections, which at the moment are done manually by experts, which fill in documents to report and evaluate defects of the tunnels. So as we could imagine, this task is very time-consuming because it is done manually by expert who also gives subjective evaluation. So what if we could turn this time-consuming approach into something automatic? This challenge inspired our research, and actually we want to develop a deep learning framework that is able to detect and localize defects inside the tunnel. But actually, as we probably know, deep learning pipelines are data hungry, and we know that this problem of data scarcity and costly. So our contribution here is let's say, step 0. We propose a methodology for the creation of high-quality labeled images at a dataset in the context of tunnel environments, where basically you can train a deep learning framework for several computer vision tasks like object detection, instance segmentation, and image classification. Let me give a brief explanation of the journey here. We will see the phases of the data acquisition, how we prepare the images for the annotation phase, how we use the ESTAT model for ESTAT software for the annotation, and we come up with a dataset that is Microsoft Rocco consistent. And finally, we will close the presentation with how we benchmark the dataset using 3 instance segmentation algorithms. So the first step is the data acquisition. So we acquired the images with a mobile laser scan. This actually is a common data collection approach in tunnels because there is poor lighting conditions. So the 360-degree rotation of the laser is able to capture the entire vault of the tunnel and the road, providing us the so-called unwrapped panoramic view of the tunnel, which is stored in this .tif file. We couple these images with the on-site visual inspection, which is this report and other images that will be used during the annotation phase. The first step of the image preprocessing actually is to split the entire wall tunnel in these segments of 20 meters that, according to the regulation, are called concho. It's important to stick with the regulation because the classes of attention is defined for each concho. So this is our objective in the end. So then we remove the road part, which has these black lines on the side, and we actually found beneficial to improve the quality of the image, applying some gamma correction to the base image, basically. We split the processed image in 6 patches because this improves the efficiency of the labeling, and these patches are the input of our annotation system. To annotate the image, we use ESTAT software, which is a semi-automatic segmentation tool based on SEM, segment anything from meter. So we use the patch, the report, and the image to correctly identify the position of the defects inside the image and annotate at pixel level the defects. In the end, we come up with 5 classes. This column here, new class. In the beginning, we tried to actually annotate each defect according to the guidelines. The guidelines provide actually 61 types of defects divided in 12 categories. But after implementing some tests, we found out that the models struggles to actually classify each subclass. So we try to merge these subcategories, and we come up with these 5 types of defects classes. So Microsoft Coco format consistent means that basically we provide a PNG image linked with a JSON file. Our JSON is composed of two main keys, the info, which describes the images, and the object, which is this list of defects that we annotate. Actually, at the end of this phase, we only have 306 images, so it's impossible to train a deep learning pipeline with such few images. So we decided to furtherly crop the images in 6 non-overlapping patches and centrally crop to a resolution of 1024 square. We choose this resolution also to balance memory constraint and segmentation accuracy. And in the end, our dataset counts 1,800 images. To benchmark our model, we utilized the three really common state-of-art instance segmentation algorithms listed here. The models are evaluated based on the average precision, and we let the model train for 100 epochs using Adam W optimizer, and all the other hyperparameters listed in the paper are let as they are written in the paper, basically. The table here shows the result considering the best models. Best model is the one that performs with the highest AP mask on the validation set. Actually, as we can see, all the models fails in recognizing the crack. This is because this class is underrepresented in our dataset. But we claim that if we merge our dataset with an existing one, there exists plenty of dataset, including concrete crack damages, we are able to fill this gap. Different reasoning is for corrosion. We will see later a visual example. Actually, this class is mistaken for a C-page. The models in general perform modestly on C-page and spooling. This is a visual result of the prediction. We have in the first two columns the raw image and labeled images, followed by the prediction of the models. If we focus on the first row, actually, I don't know if it's visible, I hope. These are two corrosion defects, okay? So if we look at Cascade, here Cascade, it's not visible, but trust me, is able to correctly identify the area of the defects, but actually mistakes the label. So here is a C-page. So the prediction is C-page. And we found this behavior also for mask to former here. So in conclusion, in this work, we propose a methodology for handling high-quality images in the context of tunnel environment. So we propose this methodology to create a dataset that is suitable for developing deep learning pipelines according to the new Italian regulation. And as a future good developments, we first will try to fix the class imbalance specifically for the crack, merging the dataset existing literature. And since our objective is to forecast the class of attention, another important step is to also try to quantify the severity of the damage, because it's a key indicator for, for the prediction of the class of attention. And this actually ends my presentation, so thanks for your attention.